Okay, our final speaker before the break is Jerry Tjiputra, who's at the Bjerknes Institute for Climate Research.
Yes, thank you very much. Also thank the organizers, Mary, Heather, for inviting me to these wonderful workshops. And it's a real treat to be in workshops in Woods Hole this week. Quickly, this is a doodle from the report, Summary for Policymaker Report, The Ocean is Losing Its Breath. What's interesting is from the previous two talks, we see a lot of mentions of circulation and oxygen. And from this doodle, you don't see any other circulations here. Actually, on the whole report, there's only one mention of circulation of 50 pages here. So in this talk, I'm going to go a bit more concentrated from the global perspective, try to look into the basins, wide variability here, and focusing in the North Atlantic. And I'm going to show how oxygen can be used, or has potentials to be used as a proxy for identifying circulations and ventilations variability. I will start with showing animations here as simulations from Norwegian Earth System model. This is an idealized simulations going from pre-industrial CO2 with rapid climate change up to 4 times CO2 at 1% CO2 per year, and then going down again to the pre-industrial level. And then it's extended again for 200 years. Here we got sections of temperature, lower left dissolved oxygens, and AOU on the lower right. Just to give an idea how these parameters will evolve with climate change. Let's see if I can get this started. So you see this, as the CO2 goes up, you get warming, and then the temperature in the upper ocean starts to warm up. This is the ventilation regions, also pushing the warmer water mass down. The structure is pushing down following this warmer water entering, also with the oxygens, because of this reduction in the solubility. But as it gets cools down and returned again to the pre-industrial level, the model actually simulates a recovery of the circulations. So the circulations, what happened during the highest CO2 period here, you get a slowdown in the Atlantic Meridional overturning circulations, and you get a shallowing of the overturning structures. But towards the end, it recovered again. So if I show here the snapshots from the beginning, where the amok is still quite high in the model, this is the structures looks like. And then when it's at the peak of the high CO2, get pushed down, it starts pushing in warm water into the interior, also with low solubility oxygens into the interior. And towards the end, when the amok has recovered again, the structure has sort of recovered to the pre-industrial level, the temperature structures deviate from the pre-industrial level. On the other hand, if you look at the dissolved oxygens and AOU, they're actually pretty close to the pre-industrial structure. So this is just to illustrate the close link between circulations and oxygen. And in fact, this is not new. More than 10 years ago, Brennan et al. Shows the strong relationship between meridional overturning circulations and AOU in the Atlantic. And Andreas mentions this, that once you go below the upper oceans, below into the interior, most of the variability or the long-term trend in the oxygen is driven by non-solubility effect, which is the circulations. Looking at regionally, so Herlakar et al. Also look into the Indian Oceans. They see that this variability in the oxygen trend is largely contributed by ventilations or circulations variability. So the questions I like to pose then, can we use oxygens now that we know there's a strong link between oxygen and circulations? Can we use it as to provide an early warning for circulation or ventilation change, particularly in the interior oceans? And if we have good confidence in that, how soon can the projected future circulation change be detectable using the present monitoring system of oxygen? And for that, in this exercise, I focus on the North Atlantic subpolar gyre regions. So the reason is, so these regions here, the subpolar gyre, the reason is because this is a key gateway for the oceans overturning, transporting water into the interior, and model simulations has shown that this is regions that is sensitive, or the circulations is sensitive to climate change with, to be a slowing down in the meridional overturning circulations. We also have quite good observations both hydrography and oxygens. And from the modeling predictions, we also know this is also regions with good predictability skills. And for the detections study, I used the concept of time of emergence. So Matt already mentioned this. This is essentially, for example, if you have a time series of oxygens going back to the pre-industrial level, and then you see a forced trend of warming, you get the deoxygenations. Behind it, you have this envelope of natural variability. So time of emergence is essentially at what time in the future where we see this, whether it is a trend or whether it is the actual state escape from this natural envelope. So several studies have looked into this time of emergence, Matt's paper, Keith Rogers, just to name a few here, also Stephanie Hansen's. But most of this paper has looked into the upper oceans or the surface. For the oxygens, mostly has looked at the thermocline levels. For example, here from Stephanie Hansen in 2007, look at the temperature, pH, surface primary productions, and oxygens. The oxygens here is between 200 and 300 meter depth, so it's still in the upper oceans. If you look at the North Atlantic, most of this region shows the time of emergence a bit late, towards the end of the 21st century. pH is earlier because we know the oceans is acidifying due to the uptake of CO2 very early on. But if you want to look at the circulation change, you don't want to look at pH, you want to look at variables, hydrography, or, for example, the oxygen. So the argument is that when you look at this time of emergence, which is the ratio of the long-term trend and the natural envelope, you have this kind of structures in general. You have large variability near the surface and very low in the interior. And the signal is very large in the beginning or in the upper oceans, but none of the signal in the interior. And you have something like this of the time of emergence profile. But as the climate change progress, then you see the trends start to propagate to the interior, but the variability still remain quite small. And then the hypothesis is that the time of emergence in the interior will be pushed towards an earlier period. So again, showing this example again from the CESM time series of oxygen simulations from the historical towards 21st century under RCP 8.5. This is a surface oxygen anomalies in these green star locations. You see this large variability back to the pre-industrial and the historical, and then you start to see this pronounced trend into the future. You can compute the time of emergence to be, for example, here 2078. But if you go to the deep oceans at 1,500 meter depth, you see that the natural envelope shrink considerably. And so even though you have this trend that is weaker than the upper oceans, because of the envelope of the interior oceans is relatively stable, you don't have seasonal variability, you don't have annual variability, then it emerged relatively early. And this is what we argue that it can be used as an indicator for interior circulation change. So here, for example, the time of emergence is about 80 years earlier than the surface layer. So this is from CMIP 5 projections of time of emergence. One of them is temperature, one of them is salinity, and one of them is oxygen from the subpolar North Atlantic. So I didn't label this, so I'll let you guys predict a bit which one is which. So one of them has a very late time of emergence. One of them you get an early, but more in the south than a bit late in the northern. So it's not a very good indicator. This one is very early for the whole subpolar gyre. So this is the temperature, salinity, oxygen. Very different from one another. If you look at the mean average of time of emergence, salinity is very late. The feature temperature is in the middle, and oxygen is actually very, very early. And most of the regions showing red here, which is already can be detectable as soon as we see this change in the circulations. The reasons we argue that the oxygen is good indicator for circulations compared to salinity and temperature is salinity mostly captures the circulation structure. I'm assuming here that loss of sea ice has very little impact on the structure or salinity in the interior. Temperature has an impact of the RC gas exchange and warming. Oxygens, on the other hand, you get another extra signal coming from the ventilation rate. As the circulation slows down, then you get more AOU, which is effective concentrations in the interior. So you have a stronger signal on the oxygens. when circulation changes compared to temperature and salinity. So we want to look at the model on CME 5 model. But before we look at the CME 5 model, Matt already mentions that there is this natural variability and that's very different from model to model. And we want to make sure that this model is able to capture the natural variability that is observed today before we do a long-term projections. And to do that, we look into the observations from all of oxygen's observations in the interior subpolar North Atlantic that we can get our hands on, from Godofferson's 2, the World Ocean Database, and a more recent subpolar gyre data from University of Bremen. So this is a bit extended data than the one that is shown by Sonka Sminko paper. And to study the mechanisms, we use an offline force biogeochemical model. So this is like an Earth system model, but forced with reanalysis. And then later on, I will show you the predictions from the CME 5 models. This map shows the observational coverage. As I mentioned, this region is well covered in terms of the observations. So the color shows the number of unique years with existing observations in the interior below 1,000 meter depth. So this is from 1961 to 2016. You see in these regions is actually very well observed. So this is a good location to study this, the time of emergence and the circulation's pattern change. And plotting the time series of oxygens in this depth at 1,500 meter. So the observations are shown in the blue circle. So Smitko data goes, I think it stopped at 2010. So if you look at the North Atlantic in these locations, they shows there is no significant trend, which is consistent with what we've shown here. And and then the red line are from the force model. So first you see there's a pronounced multi-decadal variability. Again, emphasizing again the previous talk, the importance of natural variability. And the other thing is the model and the observations match quite well in terms of reproducing this multi-decadal variability. So next we want to elucidate what are the driver, what's the mechanisms driving these variations. And we've seen that this is correlate quite well with the North Atlantic subpolar gyre index. So this is the index to measure the strength of the circulations along the subpolar gyre. So during a period of an dominantly positive gyre strength, we tend to see positive anomalies of oxygens, both in the model and in the observations. And then during a period of an extended negative gyre circulation strength, you see a negative oxygen anomalies. And we see this quite pronounced too in the interior from the model. So this is a vertical profile across these locations, across these regions. You see that during a weak gyre, you have tendency for negative oxygen anomalies, and strong gyres, you get the tendency of positive oxygens. But near the surface, because of the interannual variability and the signal cycles, then these signals sort of overlap each other. It's not so pronounced. Whereas in the interior, at 1,500 meter, you see this very, very contrasting oxygen concentrations during strong circulations and during weak gyre circulations. And in the contour line here, I'm showing the winter mix layer depth from the model. So what we see also during an extended strong circulations, we see a strong winter mixing and a bit wider winter mixing area compared to the period where there is weaker gyre circulations. So it seems to be related to the ventilations coming from the Labrador Sea. And to look further to this, we did a water mass properties analysis. So we are interested in this box here. What are the properties and what control the variations of oxygens in this box here? So first we go to the lab sea, into the interior in these regions, looking at what's the water mass properties. From the observations, we see that the water mass here are generally cold, freshly ventilated, so they are high in oxygens and low in oxygens, low in AOU, also low in salinity. And then we move to the south, just south of the subpolar gyre. We see a very contrasting water mass characteristic with warmer water mass and low in oxygens, plus high in AOU and higher in salinity. So going back again to this box here, contrasting what's the difference between a strong gyre and a weak gyre circulations period, During a strong period, the water mass in this box resembles strongly water mass from the Labrador Sea. Whereas during a weak gyre circulations, this sort of the mix between water mass from the Lab Sea and water mass coming from the south. From the model also support these results. So during a strong gyre circulations, we have this less stratified Labrador Sea, and you see this steeper isopycnic layer that transfer more water mass from the Lab Sea into the subpolar interior, whereas during a weaker gyre circulations period, you tend to have a flatter isopycnic layer, and the water mass sort of a mix between what's coming from the Lab Sea, Irminger Sea, also from the subtropical. So process that we identified here is that the gyre variability is an important dynamic controlling the oxygen anomaly in the subpolar interior that is related to the mixing in the Labrador Sea and the advections of whether it's a newly ventilated or an older water mass going into these interior oceans. So when we look into the projections, we want to study whether all of this model are able to capture this dynamics. So they don't capture the phase accurately, of course, because they have their own internal variability. But for the pre-industrial period, we can identify period of strong circulations and the weak circulations and do a decomposition analysis and identify which one that actually captured this dynamic properly. And only 3 models actually out of the CIMI 5 models that we analyzed. Those are the CESM, the HATGEM model, and the MPI model. And all of this model actually shows a declining in the gyre circulations. So if you look at the EOF or the sea surface height, the principal component, the first one is a dominant declining of the strength of this gyre circulation strength. And just looking at these 3 models, the 3 best model in terms of simulating the dynamic, they also produce the climatology quite well compared to the observations in terms of the oxygens. This is sections across the North Atlantic. Oxygen concentrations, AOU, and O2 SAT, the solubility part of the oxygen. And then this is the difference, the projected change into the future. So we see a deoxygenations everywhere in the interior, projected by all of this model, and mostly resemble the change in the AOU. Again, the changes in the circulations and the biology, and only a little bit coming from the solubility impact in the boundary of the subpolar and the subtropical. But most of the structure of deoxygenation is coming from the AOU. In this case, we argue this is the circulations because the biological impact usually only goes into the top 1,000 meter depth. So this large signal must come from the circulation change. And just so if you look at the time of emergence from the CIMI 5 models, you also see this very early time of emergence coming that seems to originate from the Lab Sea and then propagate southward to the interior. And you see clearer here, surface map of 1,000 meter depth and 1750. Here the time of emergence is very late, but you already see very early in the Lab Sea near the surface, and it's propagate into the interior and extended southward. So I've shown the time of emergence showing when it's escaped the natural variability. Now going back again to our idealized simulations here with rapid warming and rapid decrease, I want to know whether we can actually see whether the oxygens can also be used to study recovery. So I've mentioned that the AMOC going down, weakening, and then going up again as it returns to the pre-industrial CO2 level. So we have this so-called time of emergence when it escaped the natural envelope. And then you can also estimate the period when it starts to entering again the natural variability envelope and remain there for a long period of time. So we call this the time of recovery. And from these simulations, we can see that for AOU, going back again, so the recovery period is roughly about 300 years. So from the AOU, actually the ventilation region shows a recovery period similar to the expected, about 300 years. Whereas for temperature, they don't actually show a time of recovery until towards very far away towards the end of the simulations. So the questions again, can we use oxygens to provide early warning? Based on this exercise, I would argue we can. And how soon can the projected future circulation change be detectable? We also argue that as soon as we see a persistent long-term trend of force deviations from the natural variability, we should be able to detect the circulation change using oxygen. Yes, to summarize, our multi-decadal timescales, we identify important processes controlling the dynamic, which is the gyre variability that affect the Labrador-Sea mixings, and then the advections, the source of water mass entering to the subpolar North Atlantic. And we've seen that all of the CMIP 5 models shows a declining of this strength into the future. This leads to deoxygenations in these regions, which is twice than the global mean. And the time of emergence of oxygens is much, much earlier in the 21st century than temperature and salinity. And hence, we argue that interior oxygens can be used to detect anthropogenic induced circulation change and recovery. And I was asked to pose a few questions for the discussions. One is, I think our confidence in oxygens as proxy for circulation strongly depends on these assumptions of Redfield ratio world. The question is whether this is supposed to be true, that it will hold today and will continue holds into the futures. Secondly is that we have also advanced considerably in terms of modeling and understanding of oceans, oxygens, and circulation's relationship. It's a time for us modelers to be more involved in the observational community, providing more guidance and information in guiding future monitoring strategy. With that, thank you very much for your attention.
Thank you. I want to first correct my mistake that we do have one more talk before the coffee break. And I also wanted to give you a reminder that it would be really helpful to the younger members and new members of this community if you could introduce yourself before you ask a question. Thanks.
Thank you. My name is Brendan Carter. I'm from the University of Washington, and I just wanted to thank you for your talk. That was really nice. I had a comment and a quick question. The comment is that it's pretty common to have time of emergence and time of detection kind of used interchangeably, but there is an important distinction, which is that time of emergence kind of assumes that you have a perfect observational record, as you do in a model, but that's often not the case. So there's kind of another uncertainty that we have to consider, which is how well we've observed and kind of mapped that. Getting on to the question, so I'm used to seeing time of emergence/detection done as kind of trying to pull out the long-term signal from a lot of time scales of noise. But one of the really interesting things I thought about the first part of your talk is, if I understood correctly, you were looking at one of the time scales of variability as your signal itself, decadal variability. So I was just curious, what was the cutoff? Like, at what point did you declare some forms of variability to be noise versus some to be the signal that you're interested in?
Okay. So to your first comment, I think you are right about the measurement accuracy. And just so happened that the oxygen is pretty accurate from the measurements. I think it has 1% error uncertainty, if I'm not mistaken. The observation, people can correct me. So it's actually a good tracers to do this. And what is the cutoff? I think it varies from regions to regions. So for this time of emergence method, we're actually using a quite robust method in that way, in the sense that we only compute the trend starting from the time we know that there is a consistent long-term trend of negative. So we don't start the trend from, for example, 1990 or 1950, so not just randomly choosing the period. It has to be a period when we see a starting consistent long-term trend. So for these regions, the multi-decadal variability is small compared to the long-term trend because of the circulation change is quite significant in the future. May not be the case for other regions. Thank you.
Hi, thanks for a nice talk. I'm Jamie Palter from the University of Rhode Island. And I'm wondering, I'm glad you ended with this schematic, because we found, and I think the next talk might allude to this, that you could decompose the changes in oxygen into changes due to the N member, oxygen, like at formation, and the change is due to the fraction of those N members. So in this case, like subtropical waters, which have very low oxygen, and subpolar waters, which have very high oxygen. So I'm wondering if you had a way, if you perform that and could see whether this is changes in the oxygen formation or changes in the water mass fraction in these regions.
The answer is no, because I think from the CMIP 5 model outputs, we cannot do that. But I think in the next round of CMIP 6, we will have more variable like the preform oxygens and preform phosphate that will be able to characterize different source of water mass coming from. I think that will be possible in the CMIP 6 model output, but not from CMIP 5. Yep.
Thanks, Ben.
Thank you.